And I said, just go to the, go to the thing, this thing right here. And she said she couldn't find the video. She was looking for Calculus 1. I think it's Calculus 1. Yesterday. Hmm. Yeah, yesterday's Calculus 1. Here it is. I said, it's right there. And she said it wasn't there yesterday. And then I realized that YouTube doesn't post them to the home tab until like 24 hours after they get done. So the videos will be on the live tab until then. So if you're looking for a video and it's, I know if you're watching this, then you must have found it. But anyway, it's under the live tab. There it is. So you can see, here's my morning. There they are. And this, we are live right now. Some of you have figured this one out that you could be watching. Don't watch it now. It'll be like there'll be feedback or whatever. There's a delay. So anyway, there it is. So make sure, oh, it's actually here now. But yeah, when it goes, like it goes here. So these are this morning's videos. So this afternoon, after we stop, this one will just be found on the live tab, at least for a day. And then tomorrow, it'll go over to the home tab. I don't know why. I should probably change the links on Moodle, but I'm too lazy to do that at this point. So that's the situation with YouTube. So what about Instagram? Okay, we'll get there. I guess I was premature with the Instagram thing. We're going to be studying systems of differential equations. So a system of differential equations is a set of two or more differential equations that are related to one another. We've had this before with these predator-prey systems, and this is a review. Don't write any of this down. This is just for your entertainment, and then we'll get to the Instagram matrix, and then we'll have to write stuff down. So anyway, the idea here is that you have something like foxes and hares. They interact, their species interact with one another. The foxes eat the hares or the rabbits, and the rabbits hope that the foxes don't eat them. Anyway, down here, you might have a system where the rabbits, the change in rabbit population with respect to time is related to both the size of the rabbit population, because rabbits reproduce. You know how they say, they're what is it called? They're reproducing like rabbits. Isn't that a thing? A saying? Okay, I don't remember. And then if you have rabbits and foxes near one another, the foxes eat the rabbits, and so that's where this negative comes from. Over here in Foxland, the foxes will starve if they don't have rabbits to eat. And so if you don't have any rabbits, you're going to be dying out, foxes, sorry. But then you do have this saving grace of the rabbits providing you with nourishment. And so if you have rabbits and foxes near one another, you have this additional term. So the foxes actually live. Anyway, I think I showed you this picture before that this is data from Canada of hares, rabbits, and lynx, which are basically bobcats, but that's what they call them. So it's a type of bobcat, or mountain lion, all the same thing, apparently. But anyway, so you'll notice here that over time, these two populations have interacted in this predator-prey situation where when there are, let's see, what's going on here? This is the lynx. So these are the cats. I think that this is where we should start the data. Not a lot of rabbits around here. And so the cats, they start dying off. And then when the cats are dying off, you have this kind of lag where, oh, look, the rabbits, they can start reproducing, without any fear. And then they get up to some peak. It's not perfect here. But then once there's a lot of rabbits, the cats start eating the rabbits and they start going nuts. And I don't know why maybe there's a cold spell. But generally, there's a lag. You have a peak for the rabbits and then a peak for the predator. And then the rabbits die off, and then the predator dies off. So it kind of follows that. You can see that along here. Not perfect, but remember, we're doing a model. This is a model of the true situation here. And if you graphed these, you would find, well, once we can solve them, we'll be able to graph them, and you'll find that you do get graphs that look like this. This is too complicated for us right now, too much. And so we're going to turn to Instagram, and we're going to talk about Brad and John's Instagram accounts. So suppose Brad and John are competing Instagram influencers, and they're going to gather followers or lose followers based on how good they are and how bad the other person is. So when John is doing great, it may be that Brad, it loses followers to John or so on. And so here's the situation is the change in John's followers is equal to 2 times the number of John's followers minus 2 times Brad's followers. So there's a relationship there between John, Brad, and the increase or decrease of John. Brad has a similar situation that the change in Brad's number of followers is going to be the negative of John. So if John is doing well, Brad's going to be, not going to be is going to be eclipsed. But then plus 3 times Brad. So every time Brad has a follower, they go out and they get 3 more followers. So apparently Brad's followers are more into Brad than John's followers are into John. So now we want to know what's going on with this situation. Now here what we're going to do is we're going to represent this with a matrix. So a matrix is just a way of compiling or representing systems of equations. And I have here a system of differential equations, but if you're familiar with matrices, you're going to have no problem with this. By the way, has everyone had or is having linear algebra? Has anyone not had or is currently in linear? Really? Really? Wow, maybe this should be a prereq. No, it's for next spring. Yeah, you got to have it at some point. Same with you two. You're going to take it. Oh, over the summer. You're doing summer linear? What in the world? What, did you follow Brad on Instagram or something? Oh, and John. Okay, so you've contributed to both of these increases. That's good. Okay. Anyway, it's okay because we're going to take it easy and I'll go over. That's why I've got this huge list because determinants you may have heard of, even if you haven't had linear. Eigenvalues, even if you've had linear, you probably don't even know what an eigenvalue is. Same thing with an eigenvector, right? Like that, it's all foreign. Literally, it's German. So, okay, so let's do this then. First of all, let's talk about what that represents right there. That there is just a concise representation of this set of equations. So I suppose I should write this down, that x is equal to this vector. And so x prime is this vector. So just so that we're all on the same page, the linear algebraists in here are going to be super comfortable with this. The rest of you, 3 of you, maybe 4, depending on the other people who aren't here right now, aren't going to be as comfortable, but it's okay. Because I'm going to at least give you the tools, the basics. So we'll do a quick basic, and like I said, if you're scared of eigenvalue eigenvectors, you should be. But what I should say about those is that even if you've not had linear, no one in linear understands them anyway. So we're all on the same page. I know this to be a fact because I was in linear algebra once and I had no idea what an eigenvalue or an eigenvalue was, or eigenvector. It made no sense until I took differential equations. And then it made sense. It was amazing. So hopefully this will at least help you understand why we care. Okay, anything else about this? Yeah, oh, you know what? It would be nice to understand that. So let me just back up quite a bit to this right here. Just a minute. Looking, searching, finding. Where is that? Is this what I'm looking for? Ah, yes, multiplication. Oh, that's not quite lined up. It doesn't matter. Okay, so multiplication. So that's the first thing that you should know about linear algebra, is that a matrix is just an array of numbers, kind of like this, kind of like this over here, that array of numbers. And I'll toggle between square brackets and curved brackets, parentheses, just, know that if you see an array of numbers, it's a matrix. Anyway, a vector is usually written as a single column of a matrix. We're not getting into anything fancy other than eigenvalues, eigenvectors here. So trust me, it's going to be okay. But here, we do need to understand the way you multiply matrices. So the way you multiply a matrix by a vector is, think about I always imagine these arrows that just magically appear kind of like this. And you're going to multiply over and down. So I'm going to multiply the 3 times the 1 and then the 5 times the 2. You see that? Okay, let me show you. There it is. So 3 times 1 plus 5 times 2, and then you add them together. So I've got 3 times 1, 5 times 2, add them together, and you get this nice total. So the total there is what, 13? Yeah, nice, easy total. The next one, you're going to go the same deal, except for you go across the bottom. There it is. So once again, whenever I multiply matrices, I always imagine this sort of thing, where I've got 4 times 1, 3 times 2. So you've got sort of this arrow and that arrow, and they just work together to give me the final answer, which is 4 times 1 plus, oh, there's a negative hiding behind the arrow there that I didn't see. Negative 1 times 2, or negative 3 times 2. Add that up. That's easy enough. That's going to be negative 2. So there it is. So that's matrix multiplication. Just so you understand what the notation is, it's just shorthand for this thing right here. So let's do that right here with this. Let's see, x prime, just a minute. I'm going to just zoom in just a bit. So this is just shorthand for this. J prime B prime is equal to 2, negative 2, negative 1, 3, and then JB. So let me actually do the matrix multiplication with this. I know it's boring for the linear algebraists here, but I want to make sure that we're all on the same page, because it may have been a couple of weeks or a couple of years since you've done linear algebra. So let's make sure we're all okay with this. Stop me if you're confused or if I say something wrong, because I know I am not a linear algebraist. Anyway, J prime, B prime, let's do that. Okay, so I'm going to do it. I'll be careful here. Look at this. I go across and down. Give me a sec here. So that's going to be 2 times J minus 2 times B. So you see how I went across and down? And then I'm going to do the same thing, but with the bottom row. Bottom row times that column, and I get negative J plus 3B. Now notice what we have here. I've got J prime is equal to this stuff, B prime is equal to this stuff, which is exactly the original model that I was trying to use or figure out. So anyway, that at least explains why we're using a matrix to make this notation a little bit more concise. More important than that, the matrix is going to allow us to solve this system of differential equations. We're going to have a solution where you can actually predict what's going to happen to John's Instagram account and Brad's Instagram account based on some initial condition. Looks to me like the next thing is direction fields. I forgot to put it on the list until I was so excited about the matrices that I completely forgot. Okay, so let me explain what a direction field is. So a direction field is similar to a slope field. You know what a slope field is? It's got those little arrows. But this one is going to tell the direction that you're moving given whatever point you're at. So I'm going to start sketching this for John and Brad. So we've got John along this axis, Brad along this axis. And let me just put a few points here. Sorry. Let's see, 1, 2. I guess we'll count by, pardon me. We'll count by ones. Pardon me. Even though that's ridiculous, I have one. Well, I guess I only have 60 followers or whatever on my Instagram account now. 61. Thank you. Thank you for supporting my influencer campaign. Yeah, strangely enough, I am being followed by MVNU Library. I have no idea who that is. MVNU Library does follow me. Okay, so getting back to this. I need that, I need this. So what I'm gonna do is I'm gonna plot points. Well, here's how this works, is I'm gonna pick a point, just like I did. You remember slope fields where you pick a point and then you compute the slope and you draw an arrow to indicate that direction. A direction field is very similar, except for now I have to compute two slopes. So let's go back here. Oh, here's my point that I'm gonna plug in. J equals 2, B equals 1. J equals 2, B equals 1. So J prime, so this is for, maybe I should do it this way. I'll make a little table. In reality, you're not going to be doing this by hand ever. Well, maybe a little bit on an exam or quiz or something, I don't know. But for now, let's do this. We have J, B, and then J prime and B prime. So let's do that. So we had 2 and 1. So when J is 2, B is 1, J prime using this is going to be 2 times 2 minus 2. So that's 2. So notice that if I have 2 followers and Brad has 1 follower, then I'm going to increase as it should be. So I will gain another 2 followers tomorrow in this condition. I don't know what the time unit is. Let's just say it's every day. So next day I'll have 2 more followers. Okay, what happens to Brad though? Brad starts off, whoops, here we go. We're going to do B prime. So B prime is negative J, so that's negative 2 plus 3 times B. So negative 2 plus 3 times 1 is going to be 1. All right, no, not bad. So I've doubled my followers, and so has Brad. And that's good. We can work together on this, can't we? Sure. Well, anyway, let's see if I can represent this in terms of this direction field. So I'm going to go up by 2. Brad is going to go up by 1. And so that's kind of like that. See, J has increased by 2. And B has increased by 1. And if you don't mind me writing that like a vector like we did back in Calc 3 or multivariable calc, that's what we're going to look, oh yeah, that's right, multivariable. You guys had to deal with some matrices. So if you've taken multivariable, you didn't take it here, and you didn't have matrices? Oh, you haven't taken it at all? How is that even possible? Okay, well, there's always the future to hope for, but you've had linear. You haven't. That's all right. You can, it'll be okay. So here, it's just a primer. We're taking our time. That's why that last thing here is homework. Homework? With the question mark. It's okay. But anyway, getting back to this, 2, 1 just means I'm going over 2 and up 1. It's like a slope, over up. Now, if I draw my lines like that, this is going to get awfully crowded awfully quick. So what I'm going to do is I'm going to just draw the slope in terms of a line or an arrow, but the arrow is going to be shortened. Maybe I'll just shorten it down so that it's, I don't know, 1/10 there, something like that. Is that all right? So I'll try to keep things proportional, but this just tells me what direction I'm going. So if I start off right there, that's where we're heading. Brad is going to gain, John's going to gain followers, everyone's going to be happy. All right, well, let's try another one of these. Let's say we each start off with 1 follower. All right, going back to 1 follower each. Okay, here's 1, here's 1. J prime is going to be, 0. That's no good. And B prime is 2? Did I do my math right? That means that I get no new followers tomorrow. Brad's getting 2 new followers? Well, apparently his followers like him more than my followers like me. Well, anyway, so that means that we're doing something like this. That's 0 in the J direction, 2, well, it would be taller, but we're going to shrink it down. So 0 in the J direction, positive in the B direction. Well, let's see. I can maybe make myself feel a little better. Let's move over up here. Let's say that Brad has 2 followers and I have 1 follower. Let's see what happens. Okay, John has 1 follower, Brad has 2. So it's kind of the reverse of this first thing right here. Let's plug them in. I know this is a little tedious, but I just want to illustrate what this means. This actually has a meaning, a physical meaning. And of course, this is a silly physical meaning, but when we start hitting baseballs, and you know, we'll get back to remember the baseball thing, day 1? We'll go back to that if we have time, maybe next week. I've actually got it in here. It's on this this particular PowerPoint. But anyway, let's plug these in. J prime is negative? Now I'm not feeling good about this at all, this situation. What's happening to Brad? Brad has 5? Wow, he's really taken off. Okay, so that means if we're here, I'm at -2, Brad's at +5. That's gonna be roughly that direction, maybe? Is that about right? It's not perfect. Now, here we differ from the days of the slope fields. Slope fields, they all went that direction. Remember, they all went, I mean, up and down maybe, but it's always left to right. Whereas direction fields, you could go any which way. So that arrow means that if I start with 1 follower and Brad starts with 2, I'm going to quickly lose my influencer account, I think, because I'm heading the wrong direction. All right, let's just try a couple more of these just to be sure that you understand. I'm going to do this one, and then I'm going to do this one, just so that we can see how this is going to shake out. And then I'll show you the whole picture, because I did it on a computer. You can do this, you can Google, find direction field plotters, and it's pretty easy to find something like this. So anyway, let's try this, 2, 2. I'll do this really quickly. Oof, I'm at 0 again. Well, at least I'm not losing anyone. And then Brad is -2 plus 6, that's +4. Okay, he's really doing well. So that's like that. Yeah, he's taking off and I'm just stagnant. And then let's do one more. Let's do this 2, 2, no, it was 3, 1. Which one was I going to do? Yeah, 3, 1. 3, 1, and then we'll go and look at the computer-generated graph, because the computer-generated graph is much, much better. So 3, 1, that means that I start out with 2 times 3 minus 2 times 1, which is 4. Ah, that feels better to me. And then Brad does -3. Okay, yeah, the tables are turned, are they not? 4 and 0, so that's just straight across like that. All right, well, I graphed this, but I graphed it on a computer with numbers that were a little bit more realistic in the sense that, you know, 1, 2, 3, and 4 followers, that's not many followers at all. It's much more realistic to imagine that either Brad or I would have thousands of followers. And so here's a graph that goes all the way out to 1,000 and negative stuff. We'll talk about the negative in a minute, don't worry. But you can see here that you can kind of plot the trajectory of both Instagram accounts given an initial condition. Like if we start right here, what's going to happen is we're going to both increase for a while, but eventually the John account is going to lose out. See how that's curving backwards towards the B axis? And if you start down here somewhere, we both Brad and John, yeah, these are fictitious. It's not we. I'm just making up names now. Anyway, the Brad and John accounts, they both seem to be increasing, but then all of a sudden the Brad account falls off and ends up at 0. There does seem to be sort of a happy medium somewhere in here where both Brad and John can succeed if they collaborate and cooperate, maybe. But that's going to be difficult, this particular line here, this line where they both end up increasing and making incredible amounts of money as influencers. Now, you'll notice I've graphed the negatives, which don't make a lot of sense in terms of influencers. Like, what does it mean to have -1,000 influencers? Or what?
The haters.
Oh yeah, they're the haters, I guess. Yeah. Okay, so maybe that's what it means. Is like, so if I let this go along long enough, then the Brad account ends up having positive, so up here is Brad positive, and the John account ends up having negative stuff, and that's no good. Same thing goes here. If we let it go long enough over here, then the Brad account has negative, and the John account is positive. So anyway, yeah, I don't know what that would really mean, but yeah, we could think of haters or whatever. Okay, so that's what a direction field is. All right, now we have to deal with determinants, because determinants are where we're going to get our eigenvalue eigenvectors. Okay, so where do I have my determinants? Fortunately, why don't I have determinants? Hold on a minute. Matrix review. Ah, here's determinants. Okay, I got it. So I don't know if you know where the word determinant comes from, like why we call it a determinant. See, the word determinant, it's because the determinant determines whether or not a matrix equation has a solution. I don't know if you realize that, but that's where that word determinant comes from. So it determines whether you have a solution or don't have a solution. Anyway, so let me show you what I mean by this. Suppose you have a matrix equation. A there is a matrix. Y is a vector. And you want to know, does this have a solution? Well, what I could do is I could write that matrix equation. So A here is just the matrix, the coefficients, A, B, C, and D. And capital Y is this vector, little x, little y. So anyway, if you multiply through this matrix by that vector, you get this set of equations. And now everyone can be comfortable, right? Because now we're at a point where you can say, hey, I did this in 8th grade. Well, if you have numbers here. Now, if you had numbers here and you did this in 8th grade, then you would know that to solve these two equations, you have two methods. One of them is called elimination. That's my favorite method, but we're not going to use that here because I know you don't like elimination. I don't know why. Why don't you guys like elimination? Who knows? You like substitution, so we'll do substitution. Substitution, you take one of these variables, solve for that variable, and then substitute it back into the other equation. Now, I know that there are 6 variables here, but they aren't all variables. The A, B, C, and D are parameters. They're just taking the place of the numbers that I have back here in the Brad and John example. So eventually we'll pull Brad and John back into the mix, but for now, just A, B, C, and D. Anyway, here's where I'm going to do this substitution. I'm going to solve this for x, and you can see that x is equal to negative b over a times y. So far, so good. We can do this. And then stick that into the second equation for x, and then we're going to solve for y. When you solve for y, you get this expression. Okay, so what does this all mean? This means that as long as this is 0, AD minus BC, if AD minus BC is 0, then y could be any number. If AD minus BC is non-zero, then y has to equal 0 for this to work. So I guess that this determinant determines whether or not you have, maybe not solutions, but whether or not you have interesting solutions. So in particular, so here's the determinant. By the way, yeah, that is the determinant there, that thing there. Here, I'll write it again there. So if you have a matrix, the determinant is just the down diagonal. This is a 2x2 matrix, by the way. I know you know that 3x3s, at least some of you, have a different formula. But 2x2 matrix, just multiply down this way, multiply up, and subtract. And it came directly. This is, I mean, if you want to know where it comes from, that's where it comes from, is that expression. Determines whether or not you have solutions. So there's the determinant of that matrix. All right, so why do we care? Well, we care because this is how we find eigenvalues and eigenvectors. Whew, eigenvalues, eigenvectors. Okay, we're going to be okay. Yeah, this is such a crash course in linear. Yeah, I think that question mark might become a frowny face, or not a frowny face. I don't know. I hate to push too fast with this. Okay, so let's do the matrix review we did. So we can check that determinant thing off. I guess we could do an example. Why not? Let's go back here to the Brad and John matrix. I'm just going to clear all of this because we don't need it. And so let's do the determinant, because this will determine the whether we have solutions in some sense. So let's do the determinant of this matrix. See if you can do it yourself to make sure that you understand what the determinant is. Okay, so let's go ahead and I'll just go ahead and do it for you. It's pretty straightforward. I'm going to highlight this just to emphasize that I'm going to do that down diagonal, and then I'm going to do this up diagonal, and then I'll subtract. So I've got 2 times 3 minus -1 times -2. So this is 6 plus 2, which is, no, 6 minus 2, which is 4. Okay, so in terms of this particular problem, that 4 doesn't have a lot of meaning. I know, it's kind of sad that I just told you that determinant determines solutions, but that doesn't determine anything, at least not for this particular problem. We're going to get to where the determinant is important momentarily. Okay, so there's matrices, there's determinants, now eigenvalues and eigenvectors. Okay, so, whoops, where are we going with this? There it is. Okay, I want to point out some features of this particular picture. One thing you might notice right off the bat is that most of the solutions, let's start right here, let's say, most of the solutions that you can imagine are going to curve one way or the other. And even if we go like here, let's start right here, that's going to be a solution that kind of curves downward. This one curves that way. Here, this solution curves upward. If you start back here somewhere, that solution is going to curve down this way, even though it's ridiculous to think of, well, maybe it isn't so ridiculous. So if we start here, we could curve that way. But notice that they're almost all curves, except for 2. There are 2 solutions that are not curves. Technically 4 solutions that aren't curves, but 2 that I care about. Well, I don't know. You've got this one that goes straight this way. And then you've got this one that goes straight this way. So you've got 2 solutions that go straight, that go in one direction. Now here's the thing about these 2 solutions. I know you're thinking that there's these other 2, but they're just mirror images of the 2 that I drew. Oops, that one just disappeared on me. Oh, now it's doubled. Anyway, so we've got these 4 or 2 solutions. I only care about 2 of them. What's special about them is if we're at one of these points, so let's say we're sitting on this point, then the vector that I get, so let's see, this is the point, we're going to just call this xy. Oh no, I got to use b, don't I? B and J and B. Let's do J and B. Okay, so this is the point JB. Well, it turns out that the vector, whatever direction I point, that direction will be in its parallel to this vector down here. Notice that this is special because this vector starting at the origin and ending at that point is pointing the same direction as this vector, which is the vector that I get when I plug A times the vector JB. So JB points the same direction, so I could do a K here, as the vector, the matrix A times JB. Let me see if I can flesh this out. Find the next page. Why is it not moving? It's stuck. Come on. Seems to be stuck. It doesn't want to move. Okay, so eigenvalues I don't want to do yet. Eigenvectors. Eigenvectors is what I'm talking about. I know, super crash course on eigenvalues, eigenvectors, but I want to make sure that we see what we're doing. Okay, so we've got this situation. JB, let me clear that. I don't like the way I drew that. JB is equal to some constant. I'll use a K here. No, I don't want to use a K. You know what? Because this is fancy, eigenvector, I'm going to use the Greek letter lambda. Now, some of you know where that lambda is coming from. We'll get there in a sec. And this is going to be A, what's that? Why is it not showing up? No, nothing's showing up. How about now? Okay, so I'm going to use lambda for reasons that'll become more obvious as when we get, oh, it's going to show me, okay, whatever. It's little, that's okay. Okay, so I want to solve, here's the idea is I want to solve for when, I want to know what this vector is here. And so I have to solve for this particular vector right here. So I'd like to know, does this have a solution? Well, here's how I'm going to do this. I'm going to take the JB on the, it doesn't matter which one I use, but whichever one I use, I'm going to annoy someone, I'm sure. I'm going to move this one over. So I have 0 is equal to lambda A times JB minus JB. Now, one last thing that's going to be a little bit annoying is that we have this matrix called the identity matrix, which is this matrix. It's not super important. Oh, you know what? I put my lambda on the wrong side. Can I back up just a sec? I just realized my lambda is not correct. Just a sec. Let me get rid of this lambda for a second. It's equivalent to this, but put the lambda over there and put the lambda there. There. Now it'll look familiar to those who know what eigenvectors are. But anyway, the next step is to write this as a single matrix expression. So you have this. And the reason why I'm going to do that is so that I can factor out this JB here. You got JB in both of those, but the only way I can factor those out is if I have a matrix on both of these. Don't fret if you're not totally understanding it. I'm doing this mostly for the benefit of the linear algebraists who, at least at some point, learned about eigenvectors and had no idea what they were. But here we have something that we can point to the eigenvector, and it's so beautiful. But anyway, here I've got A minus lambda I times this vector JB. So just to back up to the whole determinant thing, if I take this matrix here, I can determine whether there are solutions to this equation by using the determinant. And so what I'm going to do is I'll back up one step, and to figure out what the eigenvalues are, I'm going to compute what are called eigenvalues. And the way you compute eigenvalues is you do the determinant of that matrix down there that I underlined. Okay, we're going to do this, so don't fret. And we'll do this several times before I make you do it yourself. So that's why I got a question mark here with the homework, because I knew that this preamble stuff with this systems would be a little bit tedious and time consuming. Okay, so determinant of this stuff. So let's actually do this for John and Brad. I got to be reminded, though, of the John and Brad matrix. It's 2, -2, -1, and 3. So I'm doing the determinant of this. 2, -2, -1, 3, minus lambda times 1, 0, 0, 1. Okay, so in general, what you're going to do is you're just going to compute the determinant of this matrix. You're going to take your original matrix and subtract lambda from each of the diagonal entries. So that's where this lambda is going. It's going to get multiplied by the 1 and the 1. And so, yeah, for the nonlinear algebraists, all you got to do is remember, write down your matrix, subtract lambda off of the two diagonal entries, do the determinant. So let's go ahead and do it. Okay, so see if you can do this determinant. I'm pretty sure if you just follow the arrows that you'll be okay. So there's the down diagonal, there's the up diagonal. Check this, nice. All right, so hopefully you had a chance, maybe. Let's go ahead and do it. So first of all, the down diagonal stuff, that's going to be 2 minus lambda times 3 minus lambda. That's the down diagonal, 2 minus lambda times 3 minus lambda. And then subtract the up diagonal, -1, -2. So -1, -2. So that's going to be 6 minus, I'm just doing FOIL, so just a little bit of FOIL here. 6 minus 2 lambda minus 3 lambda plus lambda squared minus 2. So far so good, not terribly bad. And then almost done. And this gives me 4 minus 2 lambda, oh, sorry. I'm going to just start fresh. This will give me lambda squared minus 5 lambda plus 4. All right, so now, so just to remind you how you do this, I know it's a complicated procedure. We'll practice it some more on Friday, but you write down the matrix, you subtract lambda from all the diagonals, the main diagonal here. Then you do the determinant of that new matrix, and you get this expression. We're going to solve this. We're going to set this equal to 0 because if it equals 0, it means that you have interesting solutions. So that's the way to look at this, is if the determinant is 0, it determines that you have interesting solutions. If the determinant is non-zero, there are no interesting solutions. Okay, so let's go ahead and do this. Set that equal to 0. You can factor that. Come on. I picked an easy, I made this easy for you. Here we go. I can prove it to you by, no, I won't scare anyone. We'll just do it. You can do it. So there, the factors are lambda minus 4 times lambda minus 1 equals 0. So far, so good? So that means that we get the following. Lambda equals 1 and lambda equals 4. Those numbers are called eigenvectors or eigenvalues. Eigenvalues. By the way, eigenvalue, it's German for characteristic value, like the thing that characterizes this matrix. Okay, so I guess it's like a word that's been formed from German and English, because value, well, maybe value is from German, but I know eigen means characteristic or representative or something like that. Same thing with vectors. So these are characteristics of this matrix, of this particular thing. In fact, this will be part of the solution that we're going to do momentarily. So not only do you get the bonus of understanding what an eigenvector is, and I know that if you're taking linear algebra, you have no idea. Well, maybe you don't have no idea. But you probably have very little idea of what an eigenvector really is. Well, we're getting there. Don't worry. Okay, so we've got two eigenvalues. We have to go back to eigenvector land. And notice that what this tells me is that if you have an eigenvector, which we do, we have two of them, then there is a solution to this matrix equation that is interesting. So let's find out what that solution is. In fact, here's what I'm going to do is I'm going to go up here and I'm going to rewrite this expression. 0 is equal to, and let me go back because I want to help you see what this is. So I'm going to write this down, 2 minus lambda and 3 minus lambda. So this here, that thing there, that is a minus lambda I. That's that right there. So that's all I've done is I've taken that, and then the j and the b, they're right there. Now I know what my lambdas are. Where are they? Where are they? They're here somewhere. Oh, they were on the previous page. So I know my lambdas. In fact, I'm just going to erase this right here. So let's get the lambdas. Lambda equals 1, lambda equals 4. Let's pick one. I don't care which. Let's use lambda equals 1. You get 0 is equal to 2 minus 1. Sorry. Let me erase that. I'll just do this. So when lambda equals 1, 0 is equal to 1, negative 2, negative 1, 2 times JB. Now, I don't know about you, but do you notice something special about this matrix? The linear algebraists sure should. Is that these two lines are not linearly independent, which means that you actually have an interesting solution. Specifically, check this out. I'll multiply across and down, and I get j minus 2b is equal to 0. And then I multiply across and down again, and I get negative j plus 2b is equal to 0. So there's my two equations. You can find the solution to those two equations. And in fact, you'll find that these are not linearly independent, which means that j has to equal 2b. And so any number, any pair of numbers where j is 2 times b is going to be a solution on this particular, I guess, thing. And so we can make a vector out of this. Let's pick a number for j, or no, pick a number for b. Let b equal 1. And so j equals 2. And so the eigenvector is going to be the vector 2, 1, the j and the b that we get here. Let me go back to the picture here so you can see this. Check it out. Well, if it would ever move, just a minute, move it back. There it is. So check this out. Right here, over 2, up 1. This is the vector 2, 1, that straight line solution. So 2, 1, the eigenvector for a system of differential equations is the straight line solution. So there's number 1 in terms of solutions. So let's see, where is that? Okay, we need the other vector. I'm going to have to erase some of this. So if you don't mind, I'm just going to do it. I know you don't mind. Some of you are completely blown away. Don't worry, we'll turn this into a formula soon. So this is partly for the linear algebraists, partly a quick primer on eigenvalue eigenvectors, but we will make this formulaic. So we're going to do the lambda equals 4 situation now. So we did 1, that's this vector over here. Lambda equals 4, I'm going to do this. 0 is equal to, I'm just taking this and copying it down with lambda equals 4. Negative 2, negative 2, negative 1, negative 1, JB. So let me write these down once again, multiply across and down. So 0 has to equal negative 2j minus 2b. And then this one across and down for the bottom is 0 is equal to negative 1j minus b minus 1b. Those are basically the same equation. There's just one of them is double the other one. So just take one of them and you find that b has to equal negative j. And so pick a vector where b is equal to negative j. So let's say b is equal to 1, then j is equal to negative 1, and there's this vector. Now let me go back to my picture, and you can see that negative 1, 1 is this vector right here, and that's the other straight line solution. So eigenvectors, so getting here to this, eigenvectors are straight line solutions. That's number 1. And number 2, eigenvector values, those are going to be related to the actual solution. So we will get to that on Friday, because we don't want to do that now, because if we do that, we'll have to have homework. And we don't want any homework. So why don't you do this. Take the time you would have spent on your homework in this class and devote it to those projects that you were complaining about at the beginning of class. So why don't we do that? And don't fret. Those of you who are still fuzzy on the whole differential equations and eigenvalue thing, we're going to come back to this and actually do a couple of examples start to finish so that you can see where the eigenvalues and eigenvectors come from. It is not as complicated as it feels. I know the first time, I remember it was all like just a foreign language, but hopefully we'll get it straightened out. All right, I'm going to stop the recording in case you have to come up and complain.